Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're fortunate today to have Ido Dagan visiting from Bar Ilan University, where he's a senior lecturer, but I told him I was going to give him a battlefield promotion to professor today for the introduction. Ido has been in the field for a long time. He was an early advocate of empirical methods in NLP processing. He's worked at Bell Labs, at IBM over the years, and at IBM he worked on combining McCord's symbolic parser with statistical methods, which I think was probably the earliest or one of the earliest attempts to do something like that. And most recently, he has been the driving force behind the RTE, the Recognizing Textual Entailment Challenge, which is something that's created a lot of energy in the field, a lot of people publishing around this area, and that's what he's going to be talking about today. Thank you.
Thank you for the introduction and for the promotion. Okay, so as Bill said, I'll be talking about the textual entailment framework, a framework that we've initiated 3 years ago. As you can see, with many colleagues, both at Bar Ilan and collaboration we have with the Trento group in Italy. And yeah, okay, we'll just start. So the theme of the talk, kind of the theme I try to put around the talk, kind of trying to take textual entailment, see what might be the next step with this kind of textual entailment paradigm, is trying to view it from the perspective of a potential framework for applied semantics, right? So the basic theme is, right, we need semantic inference, so there should be some framework for doing it. Largely, we don't, we need a framework. We need a framework to do it, but largely it's still missing. So maybe textual entailment can be a good candidate. So that's kind of the theme I try to walk through. Okay, so if we want to think of a framework, what do we mean by a framework? So we need frameworks to model levels of language. Like if you think of syntax, for syntax, a framework of doing syntax is parsing, right? What does it mean to do syntactic research, to do computational modeling of syntax? It means to develop parsers, right? And models for parsers. So if we want a framework for another area, let it be semantics in our case, what would we expect from such a framework? Okay, so I've put up 3 desiderata, which might be not completely comprehensive, but give, I think, the gist of what a framework should provide us. So first, if we look from an applied perspective, we expect a framework for targeting a certain modeling level to give us an idea of what should be the generic module that addresses this framework, right? Like with parsing, we know that with syntax, we know that we need to build a parser. We have some clear notions of what a parser output should look like, and a good model for the syntactic level should provide parsers that can be then plugged in any kind of other application. Okay. Beyond that, from a research perspective, it should give us a framework for investigating the various kind of sub-problems and phenomena within that target level, right? If you want to build models for coordination, good models for coordination in language, eventually they will end up being part of your parsing strategy. If you want to handle relative clauses or any other kind of syntactic phenomena, it will find its place within this parsing paradigm. And lastly, because language processing is knowledge intensive, it should also give us some framework for representing knowledge in a kind of unified form. Again, the syntax analogy, any kind of syntactic framework has its own formalism, own representations, under which you can represent both the information about conjunctions and about coordination, and about all other syntactic forms. Right? So this seems to be kind of desiderata for a framework, and that's not the case for the semantic level these days, right? We have a bunch of kind of isolated, scattered problems on which people are working, but I think the desiderata are largely not met by this kind of current situation. Maybe just one thing to point out, that there is a common theme probably around all these kind of areas, and that's, I would say, the interpretational paradigm, and I'll get back to it later towards the end of the talk. Right, in all these cases, people believe that to do semantics mean, okay, semantics is about meaning, so I need some representation for that meaning, some representation that I invent, basically, right? We invent word senses in WordNet, we invent classes of named entities, we invent semantic roles, and then the semantic task is map language to these invented representations. So that's kind of, even though the things are scattered and everybody invents, in every task it's kind of different types of representations, this kind of common interpretational paradigm seems to be common for all these things, okay? So I'll put up back, I mean, basically my concluding slide will again show up on the screen, these three desiderata, and we'll see whether we believe that we might be making a step in that direction. So the outline of my talk, I'll talk about the textual entailment task, try to explain how it was motivated. If we have a task in an empirical applied setting, we must have evaluation, and the dominant evaluation mode was this PASCAL RTE challenges framework that Bill mentioned. So we'll see what that means. Then to give a sense of, okay, if we agree on trying to do textual entailment, how you could go ahead and try to do it. And in that, I'll give a quick review of what we are doing in our group to model textual entailment. And that would be more like an illustrating example. So I'll talk about my own work. That's usually what people do in their talks. But it's not necessarily the only way to do it, but it'll give a sense. And then finally, I'll get maybe to the part of the talk that's, from my point of view, is maybe the highlight of the talk, because up to that point, it's kind of usually like that the screen is just near, that the monitor is, that my laptop is just near the screen, so I can kind of use my long hands and wave. But maybe I'll have to use this kind of technology. So up to that point, you know, if someone, this is kind of covered in the literature, in the last 3 years literature, so maybe someone that's very familiar with textual entailment, which I guess is nobody in the audience, you know, knows most of the stuff up to here. This is kind of like the next step where I think we might consider taking this approach that's really showing that we can view textual entailment maybe as a way to, as a framework or as kind of a point of view to look at our semantic problems. So that's what I'll be trying to say at the last part. And it's an alternative framework because things look a bit different when you look at semantics that way. Okay, so that's the outline. So we're talking about semantics. We are referring to meaning, right? That's a semantic level. And basically, so we are concerned with these two levels, the language level and the meaning level. And of course, the story is difficult because it's a many-to-many mapping, right? If we had a one-to-one mapping between these two spaces, everything would have been simple. So, you know, one aspect of the many-to-many is the ambiguity phenomena. Everybody knows and likes to talk about it. But kind of the dual aspect is what I call variability or variability of semantic expression, but that's what I mean by saying variability for short. You know, it's a sense that not only the same expression may have several meanings, but also the same meaning can be expressed in many different ways in language, right? The textual entailment perspective kind of puts more emphasis actually on this phenomena rather than on this phenomena, kind of suggesting that this might be really reflecting the goal, what we want to do, to capture this and to recognize this variability, while ambiguity will be some hurdle in the way that we'll have to deal with, but maybe the emphasis should be on this. So if you look at variability, here's an example of variability, right? Many ways to say the same thing. And if we want to start recognizing that, and that's right, applications need to recognize that, and I'll talk about it in a minute, but any kind of application that will give you information extraction or question answering that will try to approach, you know, what happened on the day would somehow needs to recognize the semantic relationship between these things. And when we are talking about relationship, you know, we can have two types of relationships. One is equivalence, right? This one and this one are pretty much have equivalent meanings, right? So I'll use this arrow as kind of representing the fact that the meaning is equivalent. And often when people talk about paraphrasing, that's what they mean. The two expressions have the same meaning, or almost for practical purposes, or at least in some contexts, identical meanings. But the more general case is, of course, that the arrow is just unidirectional. We can infer Dow ends up from Dow gains 255 points, but not vice versa, just because this is a more specific statement than this one. So the general case is just entailment in one direction. Okay, and when I say entailment here, I'm not going to refer to really a strict logical entailment, but the kind of entailment I'm going to talk about. So it's kind of borrowing the same known symbol. So the next thing I want to suggest is that indeed this kind of entailment relationship between expressions, language expressions, seems to capture the very typical, very prominent type of semantic inference that's needed for applications. In some sense, I'm going to say that that's actually the kind of semantic inference that usually our applications do when they do some semantic inference. So let's just take a QA example. If I have this example of a question, who bought overture, before I'm doing any semantics, I'm going to look for the information in some documents. In the documents, of course, it won't be phrased as a question. It will be phrased in the affirmative form. So I have to do this exercise of transferring to affirmative form. So basically answering this question, meaning trying to look texts that look like that, where whatever would fill the X slot will be the answer, right? But however, of course, due to variability, the text won't, often the text won't look exactly like that. They'll say the same thing, but differently. So suppose I have this, overture's acquisition by Yahoo surprised the market, blah, blah, blah. Okay? From this expression, I can infer that Yahoo bought overture, right? That's actually what I'm trying to do, to see that this expression entails the kind of expression I'm looking for with Yahoo filling the variable slot. So actually the kind, if based on this, if based on this text I'm going to say that the who should be Yahoo, it's because I made this kind of inference. I said overture's acquisition by Yahoo entails Yahoo bought overture, which is kind of the match into my original question. So what I really need to do here, this kind of entailment inference. And this kind of entailment inference gets repeated in many, most text understanding applications. So if I have information extraction and I want to identify buying events, and I'm going to read this text, and my IE system will fill Yahoo as the buyer slot and the overture as the acquired company slot, it's because it had to make this, again, this kind of entailment inference. Or if I do IR and I look for acquisitions by Yahoo, and I'll bring this as a relative on text, it's because I can entail from this text the fact that Yahoo bought something, right? Multi-document summarization, the semantic task, summarization, has a pragmatic aspect of figuring out what's important parts. But the semantic part of summarization is to recognize, again, that the same meaning gets repeated, and you want to include it only once in the summary. You don't want redundancy. In your summary, MT evaluation is the generated translation equivalent to the gold standard translation? Is the student's answer equivalent to the gold standard answer, etc., etc.? So we can actually see that the actual type of inference that those math systems need to do is an entailment inference. However, despite the fact that this seems to be a very common type of inference and maybe capture the major type of semantic inference needed by these applications, it's quite common that these types of inferences are approached in an application-specific domain. So the QA people talk about it in their community, and the IE people have other methods to do it. These do it unsupervised, these do it supervised. The summarization community does something to do this kind of... Everybody's trying to do something about these inferences, and this is an example for a workshop in QA. But the issues are covered are those issues of semantic inference, that are relevant for other communities as well. And this kind of illustrates this scattered situation that's also reflected in the way our community kind of semantic work is often scattered across communities. And the question is, can we find some common framework under which people from all application areas can work on applied semantics and agree what they need to do? Okay, so if we want to examine this kind of entailment option, then, of course, that takes us, first of all, towards the classical notion of entailment. And entailment is indeed, in formal linguistics, formal semantics, and in logic, of course, entailment is a very key notion. And this is the standard definition, kind of taken, from a semantics textbook. Okay, so a text, and we'll use a notation T for the text, the kind of the text from which we want to entail something, and H is the hypothesis that we want to figure out whether it's entailed or not. So T and H. So T would entail H if in every circumstance in which T is true, H is true as well. Okay, and this pretty much reflects kind of in a linguistic context the standard logical entailment. Right? A implies B. If any time, in any case in which A is true, B is also true. Okay, so it's just a standard notion of entailment. The thing to point here, for our purposes, is that this is strict entailment, right? And typically, if you find in the formal linguistics literature, you'll hear discussion, no, A doesn't entail B because there is this and that bizarre situation in which A is true, but B is not true. Therefore, A does not entail B. And this doesn't, however, in our kind of applied language processing setting, usually we want to be a bit more flexible about it. And this is an example, this is T. Does T entail H or not? So someone might start saying, yeah, I've been getting kind of incubated this vague idea, but the actual invention was carried out by someone else. Okay, so T does not entail H. While if you have a question, who invented the GPS, and your QA system based on this sentence would say, Ivan Getting invented your GPS, you would feel pretty happy about it. So what we're after is kind of a bit more loose notion of entailment, which led us to suggest something of this sort. So you would say, okay, T entails H if humans. So first step we make reference to human understanding, which is what we do in applied NLP, right? We evaluate QA, i.e., summarization by human gold standard. So, often people don't say it explicitly, we put it into the definition, but that's how we work in applied NLP. Okay, read in T will infer that H is most likely true, and this most likely, or for any, for most practical purposes is true, can be assumed to be true. That's just to capture the things such as the previous example. So basically, we would like our entailment, the definition of textual entailment or applied textual entailment, to reflect the kind of entailment inference we expect from our applications to do, and the level of most likely might vary depending on the context. In some cases you want to restrict to more certain inferences, and in some cases you allow like to increase your recall, and then you're allowed to be a bit less certain. So really what we have here is, in fact, a quite typical definition of a task that refers to human gold standard. And one thing to notice here that's going to show up along, and it kind of is implied already by this definition, is the issue of background knowledge, right? So usually when you make inferences from text, it's not just by reading the text, but by using some background knowledge, both about the language and about the world, that you imply in order to say that something is relevant. So indeed, this definition, as indeed inference from text, acknowledges that you are sensitive to the level of knowledge, right? So if we want to define entailment, it will be relative to some level of knowledge that we assume. For instance, when I say we want to kind of capture, when we do a QA system, we want to capture the kind of knowledge that an educated person has in mind. And then, therefore, we'll take educated English speakers as our annotators, and that's what we would like that's a behavior that we would like our systems to imitate. Just to show, and I won't get back into that, just to say, because often we like to model kind of most likely type of notions in a probabilistic setting, we can do it also here. So we've also proposed the probabilistic definition just to clarify what we mean if we take a probabilistic perspective for textual entailment. We would say that T probabilistically textually entails H if the probability that H of true, once I've read T, is going to increase relative to not reading T. So, I'm asking, did Yahoo buy Overture? I may have some, prior probability for believing in that statement. If after reading the text my belief increases, my level of belief increases, then I would say that to some probabilistic level, the text implies the hypothesis. Okay, and this is actually equivalent to saying that there's positive PMI. And I may refer to this left-hand side probability P that H is true given T as kind of entailment confidence that I want to attach to my entailment inference. Just to pinpoint a little bit the role of knowledge in this context, we know that what we mean by making such a knowledge definition that's relative to a knowledge base, we would like to say, either in probabilistic or non-probabilistic sense, that the text and the knowledge, we'd say that T entails H if the text together with the assumed knowledge together imply H. However, the knowledge itself does not entail H alone, right? Because if we know H already from the knowledge we have, it's kind of, in this setting, it's an irrelevant exercise to say, does T entail it? So we would do the entailment exercise saying, yeah, we infer H from T, if we assume that by the knowledge we had up to that point, we couldn't infer H yet. Okay? So that seems to be the role of knowledge. And it also precludes tautologies, right? We'll never say that the text entails a tautology because, again, we knew it already without the text. Okay. So this pretty much kind of frames what we are talking about when we want to talk about textual entailment. Okay? So once we have a task, okay, we need to evaluate it. And through a really anecdotal sequence of events, we ended up organizing benchmarks, something that would ask me 3 years ago. 3 years ago, I would say, I swear I'll never participate in a benchmark, let alone organizing one. But yeah, that's another, that's a coffee break kind of discussion. The pros of constant benchmarks, I'm not the only one talking about it. But we ended up organizing these without me planning to do so. And these were the organizations, including Bill here, that were participating in the organization of the 3. Now we are running the 3rd one, and the workshop will be at ACL. Okay, so how do we create a textual entailment data set? The whole point is, right, to try and show or indeed assess that this kind of entailment inference is generic for different types of applications. So what we did, we took several applications, the whole 7 in the first case, and we focused on the first 4 in the second and third rounds. So what we try to do, we try to collect data from the actual output of applications. So how would we collect? And the whole data set is just split to examples. All the examples have the same format, but they were originated from different applications. So for instance, how do we create examples derived from the QA application? We take a QA system, we feed it the question like, who bought Overture? Now, some answers come from the systems, Yahoo bought Overture with the supporting text. So we'll take the supporting text, which provides us a true answer, the correct answer, and we'll make the hypothesis as Yahoo bought Overture, because that's what we infer if the question is who bought Yahoo, who bought Overture, right? And this will give rise to a positive or to a yes, to a positive example. Okay, because in this case, the text indeed entails the hypothesis. However, if the question answering system would reply IBM bought Overture, because of some text mentioning IBM and Overture, but of course it's wrong, just the system got it wrong, as systems do, we can take the text that doesn't say that IBM bought Overture, take it as a text, playing the role of the text, take the hypothesis as IBM bought Overture, right? We plug in the answer in this kind of affirmative form of the question, and we'll get a negative example, right? Because this text doesn't, this text derived, that corresponds to an error made by the QA system, corresponds to a negative entailment example, okay? And similarly work on other applications, and we pretty much take examples in which the system made a good decision, a right decision, to generate positive examples for entailment, and cases where the system made a wrong example to generate to generate negative examples. And of course, the premise behind that if we have a system that will solve these right, then all these applications could use back that entailment engine to know, to filter out the wrong decisions. Yes.
Yeah, I was wondering if some of those hypotheses end up being ungrammatical. And is it because, for example, in MT?
Yeah. No. The question is clear. And by the way, please, I gave this talk at Yahoo yesterday, and it took me too long. So if you notice, I'm trying to kind of rush because I'm bad in managing the time. So, but please do ask questions as we go along. So usually when the speaker rushes, it kind of prevents the audience from asking too many questions. So this process is manual, and I should also say that not all some examples were done by kind of manual simulation, let's say, of IE behavior, because it was just difficult to get all the needed number of examples in this strict setting. We tried that as many as possible will be generated from real system output. However, it was done in a manual process, so people did fix that. It's worthwhile mentioning in this context that, inspired by the RTE, in the recent CLE or CLEF evaluation, it's the European framework for doing QA and IR evaluations in usually multilingual setting, they had what they called AVE, answer validation exercise, in the QA track, which was kind of a later add-on to the main QA task. So they had the QA task, regular, like a track QA task, and then they took the output of the systems, generated RTE, textual entailment examples, but completely mechanically. Or almost, some step was manual, but then the actual generation of the hypothesis was mechanic. And this yielded also ungrammatical relationships, right? Because, some system may give you some phrase, a whole kind of a sentence as the answer where you expect a noun phrase, and then when you plug it in, it doesn't generate a grammatical sentence. So if you do it completely mechanically, it might generate. So of course, the interface between an entailment engine and the output application, there are more things to worry which might differ between applications. Okay, and just when I'll show later the figures, just as a kind of a design choice, we use a 50-50 positive-negative examples. That should be easy to remember that regardless of the subset from which application it came, the random baseline is always 50%. So it's kind of easy. I'm not sure if, we should always stick to that policy. And these are some examples. Okay, so, here's an IE system that was run over the location relationship. Out of this text, it generated Washington. The Washington is located in Normandy. It started as a place, Washington, and broader and region Normandy as an output. Of course, it's wrong. So it generates this text as a text. This is the hypothesis. And of course, it's a negative example. Okay? A query Google goes public. This document was retrieved by the system. Okay? You can infer that Google goes public from this. Up to, assuming that the IPO does happen, it provides, in this kind of at least most likely sense, a true example. And so on and so forth. We got 800 development examples, 800 test examples, and the system get these examples, and they have to say positive, negative, and try to, to match the gold standard, the human gold standard, as much as possible. Of course, we have several annotators, control for agreement, filter out. Actually, we do filter out kind of non-consensual examples. The data set quality is decent. Okay. Apparently, we came out with this idea, and many people liked it. So apparently, it did hit kind of a sweet spot for many people. So in the first campaign, we had 17 groups, grew to 23 groups. This year, we had 25 groups. You can see about, this is, submission deadline was just recently, but, along the time, we had already, I think, over 150 downloads of the data set. So it raises interest. It seems that this kind of rationale that I was pitching in the first part of the talk seems to match the kind of perceptions that other people had as well. And there was, high interest. I just mentioned that this year our workshop will be at ACL 07. It's kind of a joint workshop also with a general paper session. And there's also going to be an ACL tutorial. So if you want to learn more, there'll be some activity in Prague this year. How did people, just to give a sense, okay, there's this test set, how did people build systems to approach it? So the dominant approach was to do kind of similarity measurement between the text and hypothesis. So I can start measuring kind of semantic similarity measurement. I can see how many words overlap. Okay, so at least for the concepts of these words, probably they speak about the same thing. I may try starting doing substitutions for hyponyms and synonyms over WordNet. I can check matching of syntactics, right? Whether the subject in the text of a certain predicate is also subject in the hypothesis. People did semantic row labeling to account for argument, row alternations, etc., and some features to identify negative contexts. So various kind of semantic pouring in semantic features or semantic kind of knowledge in order to see whether semantically the text and the hypothesis seem to match in the right direction. So whether the text implies the hypothesis. There are a couple of other kind of methods, each by a different group. The mismatch is actually Lucy's system. And there were a couple people that tried to do logical interpretation, meaning they translated the sentences to some logical form and then applied the prover. Though, I mean, it's again questionable. So these systems use logic as the representation language, and a generic theorem prover that works over, first over all the logic as a kind of matching device. But it's kind of questionable whether they were doing much more than other systems that did matching at other levels, or rather just representing, the parse tree by logical forms. So, I mean, you can represent parse trees or graphs by logical predicates, right? It's easy. Or you can go deeper, and I think it's still an issue to investigate. They probably went a bit deeper, but it still doesn't mean that they really did full logical interpretation, with quantifiers and negations interpreted appropriately. And by far, maybe the most common approach of combining these features was to take a machine learning device. So we get scores from all these semantic matching modules, and to tune the relative weights we should assign to these scores that reflect how certain or how indicative each we are with this respect to each kind of similarity score. We optimize the weighting of the scores using a classifier. So this is by far the dominant approach. Okay, how did the results look like? A bunch of systems did not that much better than, few were not much better than the baseline. Then there was a middle group, I would say, with a few kind of people at the top of the middle group. And then there was LCC, kind of about 10% about everybody else. So these were the results. And some analysis of results showed that for the first time, RTE-2 versus RTE-1, the deeper methods, the better systems that apply deeper methods, clearly outperformed shallow methods. So, for instance, unlike the situation in machine translation, where still the n-gram or the shallow models are still unbeatable, here, maybe people didn't work out the shallow methods that well, but here at least, the deeper systems perform better than the purely lexical baselines. Okay? And of course, wanting to do deeper NLP, we're kind of happy about it. Yet, most systems that applied deeper methods didn't do better than the lexical baseline. So lexical baseline kind of takes you to around 60% or so on that data set. And the question is why? And the most prominent answer that came up is around knowledge. So, okay, I may have device, but if I don't have good knowledge of what might be synonyms, which kind of syntactic constructs entail others, what should be good paraphrases, what can be inferred from what, my inference mechanism won't work. And knowledge might be captured either as kind of more explicit presentation or by the availability of training data from which you infer some, like in machine translation, some kind of mapping information. And indeed, the two LCC systems seem to be by far more heavily invested in knowledge. So the second one is Moldovan groups, which have been pretty much using entailment technology for QA for many years and acquired substantial amounts of knowledge. This is Andy Hickel at Sundar Baju groups, and they invested a lot in creating an entailment training corpus. So like in machine translation, when you want bilingual pairs, here you want maybe pairs of sentences and hypotheses to train an entailment system or to do entailment knowledge acquisition. And they followed a nice idea that Maitre presented in the first RTE, where how do I get pairs of sentences where one entails the other? So they took documents, news documents, where the title seems to have decent lexical match with one of the sentences at the lead of the document, of the article. In these cases, typically, the title is entailed by that sentence, right? Because often the title is like a brief description of the gist of the article, and then this gist is explained a bit more elaborately in a couple of sentences in the lead. And if you identify these cases, you have quite a reliable entailment case. So I think they hand-labeled, I don't know if you remember the figures, but something like maybe they hand-labeled thousands, maybe 10,000, and then through bootstrapping examples, so they kind of manually filtered a substantial number of examples, I don't remember the figures, and they, through bootstrapping, acquired a much larger corpus of these sentence pairs, and from that they trained kind of information about how likely one expression is to respond to another, kind of a little bit in the sense of people doing in statistical MT. So this seems to be the major issue. Therefore, if which kind of research directions seem to emerge, to be highlighted based on this experience? Knowledge, 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 okay? And, all methods for acquiring knowledge are kosher. Of course, we must rely a lot on unsupervised methods. And the second issue is, of course, how do you want to run your inference? Are you happy with the kind of a bag of features approach that I described before, or do you want to go for something more principled? I say just a few words a bit later about what we do about it. Okay, I won't spend much time on this one, but I just want to highlight that doing this RTE format is not the only way to go, and there are also other ways to go, and I hope the community will evolve these other ways as well, because the current way has its benefits, but it has also its limitations. Just to give a brief sense, okay, you have a task, you have a data set, how, in a bit more detail, how you can go ahead and do it. I'll tell a little bit about what we are focusing on. And of course, you need to address the three levels. Knowledge acquisition, as we've seen. Okay, how do you combine your knowledge to make some inference? And finally, something we find methodologically very important, don't wait too much. Don't develop entailment technology for 10 years and then figure out it doesn't help your applications, but rather try to do kind of a pipelined parallel approach. As soon as you have something that seems to be reasonable, try and use it and see whether it helps you. So I'll just briefly say something about that. So again, this will be a very high-level review. So we've started actually by trying to learn these kind of rules, right? So for this case, right, what reduces the risk of heart attack, to do this kind of inference, to answer the question, we need some rule of this that captures this level of knowledge. So we'll call these kind of rules entailment rules, and each side of the rule we'll call it a template. So template is kind of a textual expression with variables, where in our work we represent these as dependency tree fragments. So we use minipar parser, and this is actually a tree fragment. And we need many of those to capture the kind of both linguistic type of inferences, right? If someone is blind, they cannot see. That's kind of linguistic knowledge, right? That's the meaning of the word blind. Or more contextual things that more kind of inferences that correspond to world knowledge. Okay, I won't go very much through the details. Again, I don't have enough time for that. But basically, we've developed something that falls largely within the standard bootstrapping approach, but we kind of got it to completely unsupervised level, where you start with an input relation like x accuse y, and end up with finding templates to do that. And the scheme is indeed completely unsupervised. So this is just an example of, if you like, of the training data. So here we have typical positive pairs of the argument x prevent y. So these are good examples, right? If you wanted to have some training data for the x prevent y relationship, these would be good cases of argument pairs that typically satisfy this relation. We acquire them completely automatically. So this was not provided manually. And then having those, you can kind of extract the corresponding templates that connect these arguments and come up with a list like that of a decent number of relationships. So we really see that by these methods, there are in the high dozens typically of predicative relationships that share an entailment relationship with others. That seems to be kind of the order of magnitude that we've exposed so far. Yes.
Now you defined entailment to be directional.
Right.
Are you getting directionality?
No.
Out
So
of these
current algorithms, and by the way, the work of this flavor was done in the recent 5-6 years in the earlier by paraphrase acquisition. So the earlier work was titled was framed under the paraphrase acquisition paradigm. But as I said, paraphrase is kind of assumed to be bidirectional rules. The more general case is entailment rules. Current algorithms do not detect yet the direction. I mean, we're working on that. We had at the lexical work, by the way, ACL 2005, we had an initial step to identifying the direction for lexical entailment. Okay, so learning that dog entails animal, but not vice versa. Or bank entails company, but not vice versa. In kind of these predicative relationships, we don't know to do it yet, but I believe in a couple of years there will be people will start coming out with methods. Okay, so you can see that we can start talking about learning these things automatically. Precision is limited, but is already useful, especially if you assume that you first use it, let's say, for a limited number of relations, like in an RE setting. This gives rise to unsupervised RE. If you assume that you could filter out the wrong templates, also. Wrong rules don't. I mean, one nice thing about wrong rules is that often because they are just kind of inappropriate, in many cases they don't fire because they kind of don't match the context in which, the correct context in which you try to apply them. So it's still an open question to see how effective these rules are. Okay, now we can try and apply also lexical entailment relationship like a bank entails firm, etc. So we've done some work on improving the distributional scheme because the classical distribution scheme doesn't seem to fit sufficiently well. And we kind of added a couple of methods, finding better features and then changing the vector matching scheme from kind of a symmetric scheme to a directional scheme of inclusion. And we still need to do more. I mean, this is still work in progress. I mean, we already had a couple of papers, but there's still more work to do in these directions. And you can combine also the other type of knowledge. This follows on Marty Hurst's early 90s work from NP such as NP1, NP2. You can infer that NP1, fruits such as apples. You can infer that NP1 is a hyponym of NP. And you can acquire lexical relationships. Maybe I'll skip that. That's about kind of this bootstrapping. I'll just say. I mean, okay, maybe. Yeah, I did put these couple of slides just to show that, okay, if you take the kind of classical distributional hypothesis paradigm, I guess the point I wanted to illustrate by these slides is that, okay, we have some unsupervised methods for learning semantic relatedness of elements. However, when you want to really use it for entailment inference, what we have right now is not good enough. Okay, usually this kind of distribution similarity, it gives you some semantic relatedness, but not a strict, tight relationship as we're after in entailment. And this is just an example that's showing that when people use classical PMI, mutual information, these are the kind of features, for instance, top features you get for a word like country. They're not that great. Some of them are kind of more too specific. Some of them are too general, right? Many things have a destination or an ambition. Landlocked is kind of so specific that it would be very useful for learning. And we try to use while features like parliament, governor, population show very far down the list. I mean, it's just a list of features sorted by the PMI to country. Okay? If we really want to get tighter information, we should improve on that. And using some bootstrapping approach, we managed to improve it to this level. So we get much tighter vectors that indeed give better results. So just the kind of the lesson from this small point is that to do it right, if we're really after semantic inference, we should drill much deeper into our learning methods. I haven't seen many papers that try to analyze the behavior of the features in order to improve our methods. So that's just something that's still, to a large extent, ahead of us. Okay, I'll skip this one because the point is kind of clear. And we get some improvements in lexical entailment, and there's still work to do. But just to give a sense, these are the kind of things we are learning. So see, these are like words that entail company. It's much more than you'll find in WordNet, right? So the kind of semantic entailment that people really utilize in text is much broader than the kind of the lexicographic perspective. So that's why WordNet alone, will never be good enough. So we really need these methods. Okay, and some other type of lexical entailments, I'll skip that one. Now, beyond these kind of lexical-based entailments, things that really involve lexical knowledge, like what I've shown till now, we know that also syntax, of course, there is a syntax-semantics interface. Active entails passive, right? From a relative clause, you can infer the predicate applies to the subject in the main clause, etc., or to the argument in the main clause. So in order to capture that, we need to have some mappings. So suppose I want to match a predicate like X prevent Y. And I have this sentence, Sunscreen, which prevents moles and sunburns, blah, blah, blah. And I want to infer from that, for instance, sunscreen prevents sunburn. Okay, I don't have an exact match between this template and this construct, right? So, for instance, one thing I need to know is that when I have a predicate prevent, this is the way minipar represents conjunction. Okay, other parsers would do it differently, but again, you won't have the direct match. So you need to know that if you have an object or some relationship that has a conjunctive argument, the relationship lies both to the first, as minipar representation having to be represented directly, but also for the second conjunct. So you need the kind of rule, something like that, right? It says there's a relationship lying to a conjunctive argument also applies directly to the second argument. So if you apply this transformation to this tree, you can infer prevent sunburn. And similarly, if you had a similar rule for relative clauses, you can also infer that sunscreen is a subject of prevent. Okay? So you need to have this kind of information, and we've manually created like 50 rules or so. A linguist collaborated with a linguist that capture a variety of syntactic-related phenomena. Yeah.
Isn't the accuracy lower than you'd get from PASCAL or some other three-bank trained parser?
So there were a couple of examples why we have been using minipar, while your reason is why we hope not to switch at some point. So yeah, its accuracy is limited. We use minipar for two reasons. One, it's fast. So it's by an order of magnitude roughly faster than, the Cherniak and Collins, etc., and the Stanford parser. And the second, it gives you richer dependency structure. So in entailment kind of settings, I think many people find that it's more convenient to work with dependency structures. And minipar, by the way, as you saw, it gives you all this kind of what they can, in epistemology called antecedent information. That this is really the subject of prevents. It does things like, John promised to go, then John is the subject to go. John asked me to go, then I'm the subject of to go. It does these kind of things. By the way, this is we are in search for a better parser, but it would still be fast enough. It's kind of an issue for an offline discussion, so I'll be happy to discuss it.
Apart from speed, wouldn't the dependency analysis give you something like sunscreen prevents skin from burning in the sun, where it would tend to analyze skin as being the direct object of prevent?
So you say sunscreen prevents...
sunscreen prevents the skin from burning.
Okay.
Where you have a clause, you actually have basically a reduced clause of some sort.
Yeah.
That presumably minipar will not analyze as a reduced clause.
Yeah. While a phrase structure will, you mean? Or?
A phrase structure, if you're lucky, will, but probably not.
Depends on what it comes tagged in the entry bank.
Yeah.
I mean, these are the kind of things.
I'm saying no.
No. Yeah, these are. But I mean, exactly. I mean,
we're going to be preventing skin.
Yeah, sure.
Chris, the example you gave is exactly an example of the kind of inference rule, that's kind of on the interface between syntax and semantics that we would like to capture.
I mean, there is this stuff on semantic role labeling, which might actually have a prayer of getting that right.
Yeah.
Right. So these things are usually done as post-processes on top of the syntax.
Would you have a prayer of getting that right?
But anyhow, I mean, the kind of... so, I mean, these kind of rules just show that, I mean, you need also to work on the syntax semantics interface. And it also demonstrates, I mean, we have approached this by a manual rule writing approach, even though some of these rules you can think about ways to learn as well. But I think because the range of syntactic phenomena is not as open-ended as when you're talking about lexical phenomena, it might make sense to approach it also by a kind of a knowledge engineering approach. And by the way, we have developed an interface like you have interfaces for grammar engineering, for people that incorporate manually written grammar rules, and have developed kind of grammar engineering environments. We've developed kind of an entailment rule engineering environment, which is quite analogous. So it's in some cases, it may be easier to manually define rules rather than spending 3 years in finding a good method to learn them, if the data is more concise and kind of controllable. So I think the takeout from this part is that I think maybe in some sense for the first time, I mean, in this period, relative to older past, we may start, imagining light at the end of the tunnel. So we have more robust methods to do that rely largely on unsupervised learning, but also other methods to acquire the type of knowledge that our systems will need to do decent entailment inference, or broad-scale entailment inference. So that's my takeout, and also these kind of things, social potential for the uniform representations we are after, just like the syntacticians represent all the syntactic phenomena under the same syntactic formalism. All the types of knowledge that I have described, we have so far represented by a uniform, rather simple way of entailment rules. And actually this refers to the inference, but it seems that there's good chances of finding some uniform representations. This is the only slide I'll have on inference. We have a paper under review on that, so kind of we assume that it's still you're not supposed to kind of present everything, but the general goal of inference, and here that's not just for our work, when you take a knowledge base, I mean, if you assume you need entailment knowledge, a typical architecture for inference would be, on one hand, you'll need a mechanism for applying your knowledge, the knowledge you already have about kind of known entailment constructs. But then, in some cases, it may enable you to do kind of a proof, really bridge between the text, I mean, derive the hypothesis from the text. But in other cases, you must expect having gaps in your knowledge. Therefore, you need also kind of an approximate matching or a cost function, heuristic cost function. It says, okay, these are the type of things that I didn't manage to bridge with my knowledge. How likely it is to kind of spoil the entailment, the validity of the entailment or not. And then you end up in some kind of score and optimization, again, because you're in a heuristic setting. We have, that's what I'd say about our own approach. Our approach is to try and do all this inference without jumping into a logical representation, but rather than sticking to the lexical syntactic dependency parse representation. So basically, you could think of it as that we stick to the parse trees as our meaning representation. We do augment it with a couple of semantic features. So it's not that we have a philosophy that, we should never use semantic information, but rather kind of see how far we can get, starting with the available information before jumping to a more complicated one. And all entailment rules are thus phrased as transformation rules over syntactic trees. So basically, we have the same kind of, like in logic, the proof process, where you start from the text and using the knowledge you want to generate the hypothesis, right? Like in a logical proof system, where you have to derive the consequent. But the steps in this process is generating new syntax trees until we succeed or fail to generate the hypothesis. So that's what we do with inference. And then with applications, again, I'll go very briefly about this. We had one paper at EACL about a relation extraction kind of experiment, and everybody, I guess, knows about relation extraction. Traditionally, it's performed in a supervised manner. Taking an entailment approach kind of opens up the possibility to try an unsupervised approach for the problem. And basically, our architecture is, suppose you want to extract cases of medicines preventing diseases. So we'll start with the input templates, we'll apply this kind of entailment rule acquisition algorithm that I described. We get many rules, and now we'll try to match them using the syntactic transformations in the text. So if you find a match for some template that was learned to entail the prevent, we assume that we have an instance of prevent. We applied it in an initial experiment for protein interaction data set that is available, X interact with Y. And now, the interesting thing here, more than the results, because the results are still kind of mediocre, but some analysis that we've done is that we've seen that, at least for this data set, actually 93% of the examples seems to be kind of coverable by this architecture. So by this type of applying entailment rules and matching them, you could get 93% of the examples if you had the right rules. Okay? And this is kind of the distribution of syntactic phenomena that you need to match. I won't get much over this. This is an example of the kind of rules that TIS learned, that our system learned for this. And then the interesting thing is that when we manually examine the recall, we've seen that if we had something we didn't have at that point, we kind of already have, now we have some version of it. If you do a couple of iterations in the bootstrapping, and you assume you also have a module that knows about morphological derivation. So suppose we learned x acquired y, we also know how to map that to the acquisition of y by x. Okay, and today we had, but at that time we didn't. So we just did a manual analysis. Just with the rules that we managed to learn, we could cover 63% of the cases. So out of the 100, taking the 93% as 100%. 2/3 of that could roughly be covered. So it shows that it's not a negligible coverage. Of course, you have issues of accuracy. This is kind of current performance. So this compares to supervised approach, learning curve, which is 180 annotated abstracts, so a lot of training data. And this is what where our current supervised approach is. Again, very preliminary implementation. We're now working to analyze these results, but more carefully. And to repeat these experiments, but I think it shows that it seems to be a relevant direction. And this is just a demo, no real evaluations how you could use it for IR. Again, we plan to do more principled things, just showing you start with something on a local corpus of Israeli archaeology. On the excavating boats, you get a couple of results. If you expand it with all the rules you found, you got 24 because learn that you can discover and then search and find remains and uncover, etc., etc. So just demonstrating the direction. Okay, so this is the way we try to approach it, kind of demonstrating that might be a viable direction. So the last part of the talk, and I guess time-wise, can I take a few minutes for that? The last part of the talk is suggesting that beyond just showing that textual entailment, kind of an entailment engine might be something useful for application and something that we can imagine how we may go along and take it a long way. Can really maybe a good framework to give us the way in which we look at semantics or at applied semantic inference. How do we want to look at semantics problems? What do we want to define as semantics problem? And that's what I want to say now. I want to discuss now. So getting back to my first slide, this is kind of the common paradigm. So if we look at a typical kind of variability case, we have the language and we have our meaning representation. And the classical approach interpretations mean, how would you know that all these mean the same? Say, go through this interpretation process, map your language constructs to your meaning representation constructs. If it's the same thing, you'll find that you map it to the same thing. Okay? You have synonyms, so you ended up landing on the same meaning concept. And as said before, right, these may be various things, logical forms kind of in the complete semantic interpretation case, but it might be word senses or semantic roles, I mean, when you work on more local problems. And we should ask ourselves, the question, is this feasible? I mean, how feasible this is, and whether it's the right way to go. Are we solving the right problem? Or maybe we're inventing new problems that are more difficult than the ones we really need to solve. And what entailment perspective says about this story is, okay, of course, meanings exist. We assume that there are meanings to things, right? But it leaves that implicit, right? We don't care about representing this explicitly. We say, okay, we assume that there are meanings, but what we really care about is being able to do these entailment mappings between language constructs. So if what we need to do is recognize that these have the same meaning. Okay, we don't necessarily need to state this or to represent this meaning explicitly. That's the entailment perspective. And in the more general case, it's not the same meaning, but it might be one meaning is entailed from another. So again, the classical approach would say, let's create the interpretations of both these expressions, apply some inference mechanism at the meaning representation level, so like a logical prover, to see whether I can infer this one from this one. And if I can, it means that, the inference holds also here. Textual entailment say, as a goal, my goal definition shouldn't involve all this. My goal is to make this inference. Then the way to do it, you may use different ways. Okay, so you may try and do some direct methods, like some of those I described. Or you may try to go this way. So this way, the textual entailment framework doesn't say that this is a bad way to go. It just leaves it open. It makes the task definition theory neutral. But it does suggest, let's throw this out of our task definition, right? Because now word sense disambiguation means find the word net sense. I'm saying no. Just tell me that this is the same sense as that, okay? Or in semantic mapping. That's the issue. And I think the nice thing about it that it opens, it's kind of theory neutral. It opens up the playground for all methods to compete or to complement. Maybe some things should better be done here. Something maybe it's better to go up. How much you should go up? It very much resembles the classical MT kind of triangle, right? Transfer, interlingua, etc. for semantic inference. Okay? So that's really the issue, that this becomes the goal, but in some sense it's also kind of a touchstone for us ascending, and I have kind of one concluding, illuminating slide at the end about that, right? If I know to do it right, at least I kind of behave as if I understand. So in some sense it is a good touchstone for my model. Okay, I pretty much said that, and these are the perspectives I think I've kind of, right, the problem with the interpretation as a goal paradigm, that it's hard to agree on that, it's hard to create the annotated data sets both for testing and for learning, right, while if you go the entailment way, you remain theory neutral, the methods that you apply in the direct approach are amenable for unsupervised learning, as we've seen, and you're kind of in a sense of the proof is in the pudding test, this kind of Michael McCourt suggests this, I stole it from an email that he, kind of a supportive email that he sent me about his perspective about it. Okay, so if we take this view about how we define our problems, we can actually kind of revisit the various problems in the semantic space and try to look at them from this perspective of defining the problem as an entailment problem rather than an interpretation problem. So, some actually problems are classically, if you look at the textbook, usually when they talk about quantifier scope, all the examples are pretty much entailment examples. But, some of the problems somehow get a different definition that we used to have for them, and I'll show in a minute for the word sense disambiguation. And some new problems kind of pop up and get exposed that, we didn't show up in the literature till now, but if you try to do entailment, suddenly they pop up and you figure out, I get some new interesting problems to work on, to publish papers, so we can all be happy. So I'll just give the word sense example, right? So if we are talking about word sense in the interpretational approach, we have this, $1 million question. No set is good, and we have coarse-grained evaluation and fine-grained evaluations, but the interpretational paradigm of WSD forces you to choose and to stick to one. While the lexical entailment perspective would say, my goal is not really to say what is the sense of this word and what is the sense of this word, but rather here are two words, do their sense match, and this is illustrated in We had a paper about that, and this is illustrated in the next example. Okay, so suppose I have this question, and I need to know that this sentence, is relevant, that this sentence is not relevant, right? Why? The WSD's approach would tell, okay, find the sense of this in WordNet, find the sense of this in WordNet, same for that case. If it's the same sense, then there is a match. If not, then there isn't, right? When you take an entailment definition of the problem is only take these two senses and tell me, do the senses match or not? I don't care which WordNet sense. Just tell me whether it matches or not, whether entailment holds or not. And this generalizes also not just for having the same word, but for substituting words. Chair and furniture is the same story. So in this ACL paper, we kind of derived actually a data set, an initial synthetic, in a sense, data set for this problem, which we derived from the sense eval data. So we kind of set up the following setting. So suppose you have a source word record, and you know for a certain synonym, because this is a WordNet synonym, disk, that in certain sense is a synonym. Now you are faced with occurrences of disk. And your goal is to say in which of these occurrences the sense of disk matches the sense of record and which it doesn't. Okay? So this is actually our data set, and this is the gold standard annotation. Okay? And that's your goal that you need to do automatically. When you take this goal, you can explore the space, right? You can take indirect means goes through the word sense. And then if the senses matches, say yes. If they don't match, say no. Or you can go through directly, try and match directly. You can go supervised, unsupervised. You can test yourself classification, ranking. We kind of explored the whole space, and that's the paper was about. What I want to show is kind of maybe the most interesting aspect is to do it in the direct, unsupervised way, which can be done only if you do it in the direct way. I mean, ignoring the word senses. And what the idea was here, and it will be easier to explain on the example, right? So my task is somehow to say, is this the same sense as record? Now, I don't have any labeled training data, so the method we came up with is to say the following. This is my test sentence. If it is the same sense as record, it must have a similar context. The context here should be similar to a typical context of record. So let's take a sample. Let's say take 5,000 sentences of record and see if some of them are similar to this sentence. If there are, then probably the sentence matches. For instance, if I'll take this one, right, probably this sentence isn't very similar to typical sentences of record. So we use the kind of a KNN approach. So we measured cosine similarity between test sentence of the target word to the training unlabeled instances of the source word, measured similarity to all examples, took the K more similar, and then if similarity was above a certain threshold, we said yes, otherwise we said no. Okay? And of course, such an unsupervised approach is possible only if you take the direct approach. If you ignore, we don't have here the notion of explicit senses. We just assume that they exist and that might match or not match. Okay? And this is a result. If you use the whole sense eval data and go the supervised indirect way, you get this performance. This is where we go. This is the random baseline. And this is where we got, in this quite preliminary version of this KNN approach. It was a master thesis of one of my students. And you can see that at least at the higher precision kind of low recall range, which is often very interesting for applications, right? You don't care for the whole recall if you're in large data sets. We can get quite nice, substantial, and there's a lot of further work to improve. It really was kind of a first shot. But I think, again, it shows what it demonstrates, that once we change the definition, we don't work on disambiguation, we work on sense matching, okay, or sense entailment, it opens up the room for new approaches, completely unsupervised. Seems to address kind of the concerns that are, the WSD community is hassling with for years. And you can go this way and find variants for many other semantic problems we are concerned with. Why you have a predefined set of named entity classes? Pickup trucks may be an named entity class, right? Let's try and see whether we can say that, a certain named entity entails a certain expression, natural textual expression that represents, an entity type. For roles, let's see if, two sentences, is it the same role of the verb rather than going through giving it an explicit label, etc. And there are others, I won't get into this, but there are also other new problems that come up. So really, the sense here, this part is a kind of a substantial, if before that part, textual entailment was a nice space that kind of evolved and many people like to work with it, at this part I'm kind of suggesting for people that used to work the old way to change the way they are working. So I am suggesting here kind of a methodological change in the semantic space. So to summarize, what I've said is basically, we are suggesting that the semantic parser should become an entailment engine, and then within that framework, we can start investigating very specific and very interesting semantic phenomena, and by viewing them from the entailment perspective, first, it gives us a unifying framework to work on them, and everything would fit into this generic engine that we are trying to develop as a community. Okay? And of course, and say interpretations and mapping methods may compete, but I would like to say complement, right? Probably for some more difficult problems, we want to go higher in the triangle, but we don't need to do that we don't need to make problem harder when it's enough to solve it in a more simple way. Okay, just kind of perspective. One, this is kind of just a teaser for years ago. For years ahead of us. Just in case something like that will happen in 10 years, I could say that I already put up such a slide early on. The bioinformatics, community, or the biological kind of community figured out that they have the right representation for investigating genes, etc. So they came up with this human genome project, because they realized they need a lot of knowledge, and only if they split the work community-wise, they'll come up with it. Can we do something like that for entailment rules or entailment knowledge? And it's too early now, because we don't sufficiently understand and agree on how this information should be represented. There's still work ahead of us, but I hope that this might arrive at some point. And just as a kind of an ending perspective, before the concluding slide, I was suggesting that maybe entailment is the right way to look at semantics and to kind of model and test semantics. And it's different than the interpretational framework, but maybe it's not that semanticists used to adapt, but maybe it's not different than what most humanity does to test understanding. Right? How do we test human understanding? We do text comprehension. And what's a typical text comprehension? This example is 3 years ago, when my son was like in 8th grade, he moved to another school, and he came with me with his textbooks, and he said, I have this new kind of exercise. What do they want me to do here? And they had a text. Okay, so this is a snippet from the text. And they had like 10 sentences, and for each sentence they has to say, is this correct or not, or implied or not from the text, to test whether you're understood. So exactly the entailment exercise. And of course, what does it test? How does it test that you understood the text? By going through the variability phenomena. The text says, lies off the coast of Florida, and the test sentence says, near the United States, right? So you need to understand that off the coast is near, kind of linguistic knowledge that Florida is part of the United States, the kind of reading comprehension knowledge. So it's the variability, kind of the entailment variability, that was used to know that my son understands the text, right? They didn't ask him to write some logical forms to show that he understands the meaning of the text. And that's generally what we do also when we have questions. The question will always be described in different words than the text, right? Otherwise, the student can just do the shallow direct matching. It's only this kind of variability entailment type of inference that makes us believe that meaning is understood. Okay, so if it's good for humans, maybe it's good also for machines. And this is just the 3 desiderata, so now everybody can go back and think whether entailment kind of seems to be heading in that direction. And that concludes my talk.
Kind of late. You want to take maybe one question, or if there are any, or else I know some of you are talking to Ido afterwards, so we'll have a chance to ask him whatever questions you have.
So if there's no questions, let me just say, if you hear people in the knowledge representation language community talk about above the line and below the line, that's as a result of Ido's talk.
Yeah.
It was a very hot crowd
yeah. It's Peter Novik. He was a discussant after my talk. So I gave this talk 3 days ago in the Machine Reading AAI Symposium, Spring Symposium. And this kind of triangle, that slide with him, So Peter was discussing. He liked the idea, and he said, you know what we should do. So he was. I did put the green and red. Even though I don't really mean that the red is red. But he said, are we above the black line or below the black line? Kind of put a lot of focus on that kind of debate.
And this notion of matching seems to have caught the people who mostly come from KR quite by surprise. Then they kept referring to, well, if you take a matching approach, blah, blah, blah. So, it really did interest them to think about the problems in this way.
Right, but logical proof is also a way of matching, right? We use this kind of syntactic-based matching, but also in the logical type framework where we want to derive one object from another, right? So you can see it as derivation, or you can see it as a matching, right?
So people in this community I always see the English examples. So do people believe in the kind of universal representation of the semantics? And matching, the question is because, say, English is everything is overt, but for lots of languages there are lots of covert arguments, and the recovery of the pronominal resolutions are a big issue if we are going to just look for the surface strings.
It's even a few covert things in English, they're not.
No, but it's true that if you stick to and I really, by the way, one thing that I would hope that people would get out from the room, because I'm have two issues here. One is really the important thing is, let's take textual entailment as the goal. Let's take the interpretation out of our task definition. That's really the main thing I want to say. The other thing, of course, if you go that way, okay, it opens up options for avoiding it altogether, and that's something you may want to try to do or not. But that's, I would say, and that's what we are trying to do right now, in a sense, because I think we're not really going straight, right? We go through deep syntactic understanding and try to capture semantic phenomena, so we do climb up somewhat. But that's kind of secondary, That's the way, okay, we have now the opportunity, which I'm not methodologically, I typically tend to be a bottom-up kind of person, so we go that way. But the really important thing is on the task definition, not the methods you use to approach the task. So it's true now, so your question refers more to the second aspect. If you use the language as your meaning representation, then indeed you are kind of language specific. You'll have to regenerate those same inference rules in every language on which you work, which kind of touches also, right, for the MT story, right? The motivation for interlingua is that if you do a transfer-based approach, you need matching, you need your rules to apply specifically for every pair of language, right? So you have like n squared number of mappings that you need to generate, while if you go interlingua, you just need n being the number of languages, right? You just map to interlingua and go back. So it's kind of the same story, but sometimes maybe to get to this abstract uniform interlingua, it ends up being too difficult. Maybe it's easier to generate it separately. It's an open issue, just like it has been in MT.
Actually, just touching on that, you probably know David Dowdy and Victor Sanchez have been working on natural logic. In other words, trying to do inference actually at the level of directly at the level essentially of syntax.
Yeah.
But the question I wanted to really ask is sort of a more philosophical one. So I actually think you're exactly right that something like this entailment is a great, in fact, actually sort of, serious goal for NLP.
Yeah.
But if you actually look at how NLP has been successful, I think what we've often tended to do is actually sort of pick particular proxy tasks and work on those. And often the proxy tasks actually, indirectly have a certain approach embodied in them. So, the classic example is speech recognition, where the proxy task for us is language modeling, right? And that actually assumes a particular approach, So, we evaluate speech recognition accuracy. That's what we're really trying to optimize. But in fact, people in our crowd actually mainly tended to contribute towards language modeling. And that was assuming that you were using the noisy channel model with Bayesian inversion. And, it was actually making a particular assumption about the type of model and also the representations that would be used. And that is, you'd build language models over words, right? And maybe you can build a speech recognizer that doesn't that doesn't have that built in. But that was, I think, sort of kind of like a crucial step in actually making the speech recognition stuff work.
I'm glad actually that you raised this point, because I actually tend to view it differently, the language modeling, because...
I'm actually going to claim that, in fact, that the same things happened in parsing, that picking the Penn tree bank. Nobody thinks the Penn tree bank is right, but it's a great proxy task, right? That, the idea is that whatever the right things are for parsing, the techniques that we learn from the Penn tree bank are probably going to be useful.
But sometimes the proxy tasks, I think, are wrong, like focusing on word senses, where all that work that's gone into sense distinctions and WordNet probably may just not be useful in the long run.
But, say, for example, word alignment and machine translation, right? I mean, so yeah, you can... In fact, I actually do think the proxy tasks do tend to build in... I mean, the community doesn't acknowledge it, but the proxy tasks do actually build in... they presuppose a certain type of approach.
Right.
And, I actually wonder whether, in fact, we don't really need... I actually think, really, our machine learning techniques are really pretty primitive. I mean, basically, they're reasonably good at estimating parameters, and that's... If we can reduce our problem to a parameter estimation problem, we have a hope of actually being able to deal with it. If we can't, it's generally too hard. And so I think actually these proxy tasks actually play a fairly important role in this reduction of the problem. And it's actually the proxy tasks which wind up defining the hill for us to climb. And I think, say, for example, with word alignment, I think right now there's a serious argument within the machine translation community as to whether that really is a reasonable hill worthwhile climbing. But in fact, I actually think, that is at least how we've made progress. And, so the classical interpretation model, that is a proxy task here. Now, maybe, I don't know whether you think you can sort of do it without that, or whether you need whether there's a different one there, or actually.
Okay, so I think.
Whether you think
let me give you my view on that. So, I think from the general kind of picture, generally you have. I mean, you field is structured so that you have some, I would say, more core task, or the general, the end-to-end tasks. Okay. And they might be defined either at kind of a language level, right? Our field is kind of a matrix, right? So you have the language processing level, then you have the applications, right? So MT, for instance, is not a proxy task. It's like the complete task, right? And, alignment or language modeling are some tasks along the way. So I think you have some kind of global tasks, like, for instance, MT. Or... I would say, in a sense, like parsing as well, because these are tasks. Well, parsing in the sense of modeling a language level. If you look from the applications dimensions, you kind of have only the end applications. From that perspective, all the language modeling tasks are proxy tasks. Okay. On the other hand, I mean, it's a bit more complicated that I am kind of evolving the picture as I'm speaking, but I mean, you have the language applications, which are kind of end-to-end applications, and you may have different proxy tasks for them. You have the kind of the language modeling dimensions, which you may view either as a proxy task for the applications or, as some end goals for them. So, but overall, I think there are some global goals, and from that perspective, language model, I'm not sure if it's proxy or kind of a goal of its own. It's proxy for applications. But it may be also considered as a goal for kind of as a neutral, theory neutral, actually. I think language modeling is actually something like entailment in the sense that it's a theory neutral task, right? Just give me the probability of a string, or given two strings, which is more probable, and you can even throw away the estimate, and you have a really neutral task, right? And then it can be used and tested. The effectiveness of these models can be tested in various applications. The choice to do it by n-grams rather than through syntax or semantics is a choice. So that's exactly like in entailment when I'm saying, let's pick it the task versus which shallow or deep methods we use. So in that sense, I view entailment as like suggesting, entailment is a useful task to work on to capture the semantic level, the semantic inference level, just like language modeling is a useful task to work on to capture kind of plausibility in language. Okay, so from that perspective, I think entailment is like language modeling. Now, whether these kind of language level tasks are useful or not, the proof is in the pudding. Whether they help eventually the applications. That's why I'm suggesting, like language modeling, test that it helps the application. It's not enough just to test perplexity. Okay, so I think from that perspective, is saying, in semantics, maybe the proxy shouldn't be interpretation. The proxy task should be entailment. Okay, but to validate that this is a good direction to go, of course, we must test that entailment inference helps
so
applications.
I guess what I'm getting at is that generally the proxy tasks are things which are fairly easy to meter, fairly easy to measure, right? So, think about parsing or language modeling. I mean, they're usually automatically scorable and stuff like that.
Right.
And whereas here, whereas, say, for example, with the quality of speech recognizers and things like that, I mean, there's many different choices as to exactly what domain you should be looking at, and
but I think like the RTE showed that you can evaluate
This is
it.
automatically scored.
Yeah, but I mean, I think the problem is that there's many different. I mean, every year there's a different corpus, right? And it's a different.
No, it's
different.
Just like in QA or in TRE. I mean,
no, but a different sort of task and everything. I mean,
no,
so
it's the same task. Same task. No, the different years are just like the TRE QA or TRE IR that they release a new round every year.
But it's the same.
But they change quite a lot, right? I mean, don't they change a lot in terms of how hard they are? They change how big they are, how large.
That's what you can do, but that's the same.
How large the support?
But it doesn't change more as a QA tracks, right? Like you have
sure,
started
that's
with
fine.
factor.
That's fine. And in fact, actually, I would claim those things also aren't really good proxy.
Why don't we let you guys
Yeah,
Also
we can.
really
You would probably.
proxy tasks.
But we get a perspective. Yeah. Okay.
So
Hi.
do you want